If the Earth is round and constantly moving, how does a commercial pilot, flying a metal tube full of passengers across an ocean, hit a runway strip less than 50 meters wide with enough precision to touch down within the first few hundred feet of tarmac? Every flight, every day, thousands of times a day worldwide. Something in that navigation system is working off a very stable, very fixed reference point. And it isn't a spinning ball. Aviation navigation uses a system called ILS, Instrument Landing System. Ground-based radio transmitters at the airport send out precise directional beams. The aircraft locks onto those beams during approach and follows them down to the runway threshold. Those transmitters are fixed, bolted to the ground, stationary. If the ground beneath them was rotating at over 1,000 miles per hour and orbiting the sun at 67,000 miles per hour, the beam alignment would need constant, real-time adjustment to compensate for the surface shifting beneath the aircraft's approach path. No such compensation system exists in standard ILS documentation. The beams are calibrated once, aimed at a fixed approach corridor, left there, and they work perfectly, every time. Here's what should genuinely unsettle you. GPS, the system aircraft also use for navigation, was designed with corrections built in for Earth's rotation and curvature. Engineers openly acknowledge these corrections in the technical specifications. But ILS, the system that actually guides the wheels onto the runway, has no such correction layer. It operates as if the ground is stationary and the approach path is fixed in space. Because functionally, for every landing that has ever occurred, it is. On a flat, stationary plane, aviation navigation makes complete and uncomplicated sense. Fixed ground transmitters send fixed directional signals across a surface that doesn't move. Aircraft lock onto those signals and follow them to a runway that is exactly where it was when the signal was calibrated. No rotation compensation, no orbital velocity adjustment, no moving target, just a fixed signal guiding an aircraft to a fixed point on a stationary surface. That is what pilots actually experience. Every flight, every landing, without exception. Autopilot systems on long-haul flights use inertial navigation, tracking movement relative to a starting point. These systems accumulate drift errors over long distances and require recalibration on arrival. Engineers call this gyroscopic drift. It happens because the inertial reference frame the autopilot uses doesn't perfectly match the surface below. On a truly spinning, orbiting ball, that drift should be enormous and predictable in a specific rotational direction. It isn't. The drift pattern doesn't match globe rotation geometry. It matches the behavior of instruments operating above a stationary surface.